Hey everybody, this is Pat Nappi here from pnlearning.net, and I just took on a student who's going to be doing sequences and series in Calc 2, so I was just brushing up on some things and I came across a really good example from Paul's online math notes. I have the link here above the problem and I'll also include it in the description. This is an interesting question where we have to determine if a particular sequence is monotonic or bounded. Monotonic just means it's either increasing or decreasing, and bounded means basically that it stays between two values. You also could have bounded from above only or bounded from below only, meaning that the terms in the sequence are going to stay below or above a number. So let's check this one out and see what we can determine. So we've got the sequence here. It's n to the third over n to the fourth plus 10,000, and we're going to look at this for n values from 0 to infinity. So this is an infinite sequence. Right off the bat, we just want to try to see if we can come up with the first couple terms. So if we plug in n equals 0, we're going to get 0 to the third, which is 0, over 0 to the fourth plus 10,000, giving us 0 over 10,000. So that's going to actually end up just being 0. Now if we plug in n equals 1, we're going to get a 1 in the numerator, and we're going to get 1 to the fourth, which is 1, and 1 plus 10,000, which is 10,001. So to get the third term, we're going to plug in 2, and you're going to get 2 to the third, or 8, over 2 to the fourth, which would be 16 plus 10,000, so 8 over 10,016. And let's just do one more. So if we plug in 3, we're going to get 3 to the third, which is 27, over 3 to the fourth, which would be 81 plus 10,000, so 27 over 10,081. So what's interesting about this sequence is that it's a little hard to tell if these terms are going to be increasing or decreasing, which will help us answer the question about if it's monotonic or not. So what we should do is maybe get a decimal equivalent for this. So let's go into our calculators and go ahead and see what we get. Let's start by talking about whether or not it's bounded. So clearly all of these terms are going to remain positive, so they'll never be negative, and therefore we could say they are bounded from below by 0. Now the question would be, is it bounded from above? Is there some value that it can never be greater than? And if we look back at the sequence, we can see that this denominator is always going to be bigger than the numerator. Because you have n to the fourth in the denominator, that is always going to be greater than n to the third in the numerator, which means we're always going to have some sort of proper fraction, meaning that we'll always be below 1, right? Any proper fraction is always going to be less than 1. So we will say that this sequence is indeed bounded. And by looking at these values here, we can see that they are increasing. So we're going to be inclined to say that this is not only bounded, but it's also an increasing sequence. However, what's interesting about this is that it's not actually increasing, and you cannot tell just from generating the first 4 or 5 terms. So one of the things you can do with sequences is kind of equate them to functions. And if we can find out something true about the function, it will tell us something about that sequence. So let's take this sequence and look at it as if it were the function f of x equals x to the third over x to the fourth plus 10,000. All right, now that we've got this, let's find the first derivative of this function. Now, in order to find its derivative, we're going to have to use the quotient rule. And if you remember the quotient rule from Calculus 1, we're going to take the derivative of the top function, so that would be 3x squared. And we're going to multiply that by the bottom function, so x to the fourth plus 10,000. And then we're going to subtract from this the reverse. We're going to leave the top function alone and multiply that with the derivative of the bottom part of this function. So you would get, let's see, 4x to the third, and the 10,000 goes away. It's just a constant. And in the denominator, we're going to have the bottom function in its original form squared. If we go ahead and multiply the 3x squared on top, we're going to end up getting something like 3x to the sixth plus 30,000 x squared minus these two things multiplying. So x to the third times 4x to the third will give us 4x to the sixth, and we're just going to leave the denominator alone for now. And in the numerator, we're going to see that we have some like terms. We've got 3x to the sixth minus 4x to the sixth. That'll give us negative 1x to the sixth plus 30,000 x squared Again, we're over the same thing as before. Then if we go to the numerator here and factor out, let's say negative x squared, we're going to be left with x to the fourth minus 30,000. And here we are. We've got the first derivative of the function that we are equating to our sequence, and it will tell us whether or not it's increasing or decreasing. Think back to Calc 1. We want to do a first derivative test here and see where this function is either equal to 0 or undefined. So if the numerator is equal to 0, then the whole function equals 0. That'll get us some critical points. All right, so here's the numerator equal to 0. Of course, this is a product of two functions, so using the zero product rule, we can say that if either part of those products equals 0, then the numerator will be 0, thus the function will be equal to 0. So we just want to go ahead and set negative x squared equal to 0, and we also want to set x to the fourth minus 30,000. We want to set that equal to 0. In the first case here, we're just going to have the solution that x equals 0, so this would be a critical value for this function. And over here, if we add 30,000 to both sides, we're going to see that x to the fourth equals 30,000, and that x will have to be equal to the positive or negative fourth root of 30,000. Those are two other critical values. So that covers if our function's first derivative is equal to 0. We also want to see, is it possible for the denominator to equal 0, in which case the function's undefined. This could also be a critical point. However, if you just look at that quickly, we have x to the fourth plus 10,000 squared. So no matter what number you plug in for x, positive or negative, you're going to end up with a positive value. So there's really no way for the denominator to equal 0, which means there's no way for the function to be undefined. So these three values are our critical values. Another important thing to remember is that we don't care about this negative critical value because we're dealing with a function that we are equating to a sequence, meaning that we should think of the n values of our sequence, right? 0, 1, 2, 3, 4, all the way up to infinity. We should think of those as our x values. And since you can't have a negative n value for a sequence, we're not going to worry about a negative x value here when we're talking about the first derivative test. So the only critical values that matter are x equaling 0 and x equaling this number, and if we want, we can get a better approximation of this number. The fourth root of 30,000 is going to be roughly 13.1. And so these two critical values are telling us we may have a change in slope at either of these values. So starting at 0, and if we jump back to the first four values of this sequence, we can see that they were increasing. However, what this critical value of 13.1 is telling us is that the sequence is actually going to be increasing up to the 13th term. Once we get past that, once we get to the 14th, 15th, and 16th terms, we're going to start to notice that the function then decreases. So I just thought this was a very interesting sequence because ultimately it seems as though, right, upon initial investigation that it will be increasing. However, once you are increasing for the first 13 terms, it'll then start decreasing. So what we want to say for our final answer is that this is actually neither increasing or decreasing. It's doing a little bit of both, and therefore this is not monotonic. So that is, again, an interesting sequence, and I just thought it was worth going over because you want to run a first derivative test if you're not sure if a certain sequence is increasing or decreasing upon initial investigation. And you've got to be careful because even if you look for the first couple terms, it still may not be just increasing or just decreasing, aka monotonic. Thanks for watching. Again, like, share, and subscribe to pnlearning.net, and I'll see you in the next video.